Okay. Good morning, everyone. Thank you for coming to our talk. My name is Daniel Fernandez, and I'm gonna be talking about our project of building an open source battery for stationary storage. I am part of the Flow Battery Research Collective, and we've been doing this project along with Utrecht University with their Fair Battery project, which Josh here is representing. We're also working with Kirk. Kirk Smith is also part of the research collective. He's currently in the US, he couldn't be here, and Sanli is a professor and he also couldn't be here. Now, what is the Flow Battery Research Collective? This started last year. I have been working by myself in batteries. I'm a chemist, and I started doing research on batteries at my house since like 2019. I started a blog. And then Kirk found me, and he was like, hey, you're doing all these open source battery stuff. Let's start like a joint effort and do something more concrete. So we started the Flow Battery Research Collective to build an open source battery aiming to do solar and wind storage in the long term. In the short term, aiming to do some academically oriented kits. Now, I'm first going to talk a little bit about lithium-ion batteries because this is the battery technology that most of you are probably familiar with. In lithium-ion batteries, we're basically just moving lithium ions from graphite substrate, where they are in a more reduced state, to normally metal oxide, where they're in a more oxidized state. So basically, we transport lithium ions, and then we transport electrons, and that's how these batteries work. What most people don't realize about these batteries is how thin this thing is. So when you see this, it looks pretty large. In reality, what you have in your phone is actually this. And you have this graphite, then you have this metal oxide. In the middle, you have a separator. This entire thing, this is a scanning electron microscopy image. A cross-section, and this entire thing is a fourth of a human hair in size. This is incredibly small. These batteries are like a miracle of modern nanotechnology. They're amazing. And what separates this battery from shorting is a 5 micrometer separator that's there. It's incredibly, incredibly thin. And this is a main issue with lithium batteries. You have thousands of these layers packed and rolled together, and that is why they are so amazingly energy dense. And then, you know, this happens. And this was Moss Landing 2 weeks ago in California. They just catch fire because you get any sort of puncture in this like tiny, tiny sliver of a layer, and it all goes up in flames. These fires are not put out, by the way. You have to allow them to burn out. So like, you cannot pour water on them because they just become worse. So you just leave them there. This was the same Moss Landing fire. And now this was also in the US, in California, in San Diego. These all tend to happen in California because they have some of the largest installations. And then this was also in San Diego. And you can see how hot these fires are. These fires are quite hot. That is probably, you know, could set anything around it on fire as well. So this is why you have this huge clearance around these battery situations.
Sorry, what's that in metrics?
Yeah, sorry about the freedom units there. It's 195. Josh, you as an American, you probably have a better sense.
It's 90C.
And this is in Australia, in Germany, sorry. This is in Germany so that you can see that they also happen in Europe. They're not like only for Americans. So this is why we decided to go with working a solution that is more robust for large-scale energy storage. So we have these flow batteries that were created in the 1980s. And what you do with these flow batteries is that you don't have these solid state layers, but what we have is this cell in the middle where the power conversion happens, where we actually flow the ions. And then we have these tanks where we store the reagents. So we have something that gives electrons, something that takes electrons, and these are cycled in tanks. The great thing about this is that these tanks can be made as large as you want for storage capacity, and then if you need more power, then you get a bigger cell. So the power is determined by the cell you have in the middle. Your capacity is determined by the size of your tanks. So you decouple power and capacity, and that allows you to have a much more robust system. The more commonly studied systems are all aqueous, so they don't catch fire, and they are generally much more environmentally friendly than the chemistries of the lithium-ion batteries. There is currently no open source battery initiative at all from either lithium-ion or this field, and this is why we decided to create one. So a question is, how can this compete with the actual lithium-ion batteries? Is there any way that they can actually be viable for large-scale storage? In reality, these flow batteries are nowhere nearly as dense as the lithium-ion batteries. They are probably a 10th or even a 20th of the energy density of lithium-ion batteries. However, they have great advantages in safety, in affordability, and in cycle life, because you don't have the reagents as an intrinsic part of the system. If something breaks in the cell, you can take it apart and replace it. If some of the reagents stop working, you can replace the reagents. You can process the reagents and regenerate them if that's the case. So they can cycle for much longer than a lithium battery can. A lithium battery, any sort of small failure will be critical and will destroy the battery. In a flow battery, they are much more robust to this sort of failure. So why open source? So as I mentioned, there is no complete open source flow battery architecture. There are some open source flow battery projects that aim at producing just the cell. So there are some open source papers that show you the cell. Like, we built this cell open source so that you can build it. But then when you actually go and try to work on this, you realize there's a bunch of other little things. You have pumps, you have the reservoirs, you have the electronics that you need. All these little things are needed that they don't tell you how to build. So if you are not already at a lab where you already have everything else, it is sort of very hard for you to do. So another problem we wanted to address is that flow battery research, because of all these little things, suffers from a lot of reproducibility issues. A lot of these flow battery researchers will have completely different results, and there is no standard cell in the flow battery research community. So we also wanted to create a cell that could be used as a standard for researchers. That was also accessible to researchers in countries that do not have the resources to buy, to spend 20,000 euros to buy a single cell from like a company that sells a proprietary thing. So although we do want to sell kits ourselves as the Flow Battery Research Collective, we want to make them so that anybody can also build their own if they don't want to buy them from us. And also, no large-scale open-source flow battery cell exists. While there are these small projects that aim to give you an idea to build these small cells for lab research, there is really no open-source cell design for like a large flow battery, like what you would use in for large-scale storage. What we want to do, so we have, at the end of 2024, we completed our benchtop cell, which is small, which is what will become our kit that we will be probably selling this year or next year for anybody who wants to do this. This is all open source and available at our website. If you wanted to build your own, all the instructions are there. And we're currently testing chemistries and different materials to, when we start selling the kit, be able to sell something that has some very reproducible results that anybody could, reproduce. Then by mid-2025, we want to have a larger cell format, single cell, but larger, something that would be scalable for large-scale energy storage. And then by the end of this year, hopefully, we can have a stacking of these cells so that we can start moving towards something that would be more at the scale of powering a house rather than, the first large scale we are aiming for is this, which is something that might power your house rather than something that might power, a small town. So this is an image from Redflow, which is a company that recently went bankrupt. And this is also why we're so interested in this being open source. And it's because Redflow invested a bunch of time into this cell that is actually pretty good, but they just couldn't make the capital work. And if the technology had been open source, maybe a lot of people could have, either started other businesses or built them for themselves. So we are interested in making it such that this scenario with a company like this doesn't happen again. And then, there are very large flow battery installations right now, like the one you see there, which, you can 200 megawatt hours. So flow batteries are currently being used for large-scale installations, but we obviously are not going to go there first. Our aim is to go to something like this first, and then we'll see if we're able to go to even larger scales. Once you get to this scale, getting to that scale is way easier. The most difficult step is between this scale, the scale we're at the lab scale, and this intermediate scale. So this was our first prototype for flow battery cell, and you can see these cells have a lot of different layers. We started by building these cells out of polypropylene, but this initial design, we used silicon gaskets. We used you can see you have your current collecting electrodes there at the ends, and this is then where the flow frame is where the solution goes through, and then you have a membrane at the center separating both reagents, and it is a design where there's a lot of possibilities for leakage and problems. This was the first one that we ever built. This was resin printed, so it wasn't polypropylene, because we never got to print polypropylene well enough because it warped too much. And these are small diaphragm pumps. None of these worked. The tubing didn't work, the cell didn't work, the pumps didn't work, nothing worked. But whatever works the first time you try it, right? And this is what we use for controlling these pumps. So we use an Arduino, and then we use these very cheap motor drivers. The entire cost of this is, very low. It's probably less than, 20 euros or something for the electronic part. And this was our second try, where we had these polypropylene bodies machined, and we built those. We used now peristaltic pumps instead of diaphragm pumps. Several improvements from the first design, and this is how it looked while it was running. As you can see, nothing too exciting, just two pumps, but it still had problems. You can see that pump there is not supposed to be orange, so so leaks do happen. So this was also all in my apartment, and I'm still here, so it's not that dangerous. So then we changed to this second design, which is was made to prevent all those leak problems, and we decoupled the flowing part of the battery from the face plates of the battery. In our previous design, these plates were exposed to the chemistry to some extent, so they needed to be made from an inert plastic. Now we decoupled them, and that way we can actually have those plates built from PLA or PETG, things that are easier to print. And then our flow frames are made out of polypropylene, but the geometry is just way easier to print. The flow frame is just the thing with the barbs that's there in the middle. And this is how the newest design looks like. You can see that the pumps have been changing, and it's because we started with the cheapest possible pump we could get, and I broke it, and then we moved to the next one. And we're doing that. I've been doing that iteratively until I get to the cheapest thing that works. So basically breaking every tier of AliExpress pump I can find.
You want to give them a rating, how long it got through your scheme?
Yeah, so like I've broken them in many ways, you know, corrosion, like just the electronics fry, I mean. And this cell worked pretty well. And these are some of our first testing results. These are charge-discharge curves for a cell. And we are using initially zinc iodide as a chemistry because it is these materials are easy to source, like the reagents are quite easy to source in the EU without any need for special licenses to buy chemical materials. So we are testing zinc iodide. It's not extremely toxic. It's not it's not like you can drink it, but you know, it's fine. We cycled these for more than 5 days, and this energy density, to give you an idea, is similar. This is at like half the energy density of what like a commercial flow battery achieves. And then you can see on the other side our efficiencies through time are pretty stable. Normally in research, the membrane that you can see here in the middle, so this membrane is usually a very expensive cation exchange membrane that is, it's called Nafion, and it's expensive. And we don't use that. We use a microporous membrane that's very fancy. It's called photo paper. So we use photo paper as our membrane, and this is why our energy efficiencies and our Coulomb efficiencies are not super high. We're in like 65% energy efficiency because we do get some leakage of stuff and some additional resistance, but it's very, very cheap to achieve. And then we can also push it to higher energy densities. So this is at the level of a commercial flow battery. But you can see there's only 2 cycles here. And it's because the other stuff fails. It's not like the chemistry that failed at this point. It was tubing, it was pumps, it was like this thing becomes so concentrated. As things become more energy dense, they are usually more reactive, right? Because you're in states where things, you know, are holding a lot of chemical energy they want to release. So they start reacting with other stuff in the system, which includes tubing, which includes the pump, which includes like other stuff around. So we only have 2 cycles here because of the corrosion. And now this is the pump that we got for the next step. This is like a beefy pump. This is like the size of like a fist. This is an impeller pump. And to give you an idea, our previous pumps are going like maybe 60 milliliters per minute. This is like 6,000 milliliters per minute. So this is for the next scale up that we're doing. And so this is a little bit about how you guys can get involved if you want to help. Always trying to build a kit with our instructions is useful because nobody has tried, so we don't know if the instructions are any good. So we want to make the documentation better and want to make sure that people can do that. Also, if you don't want to build the full kit, just testing 3D printing of our 3D printing pieces works because we need to make sure that they can be printed in a lot of different printers and with different materials. Like for the flow frames, we can only use polypropylene. It's the only chemically compatible, like widely available 3D printed material that can be used. You can also help us test different tubing materials or pumps. Also building and testing larger scale cells. Our designs are still in progress there, but when we have them, helping us test that with only water because we don't want anyone to die helping us test this, then that would be very useful. And then from an electronics perspective, We don't have a BMS for managing these batteries at scale. Like in the small lab scale, the batteries don't even produce enough power to run the peristaltic pumps. The peristaltic pumps are very inefficient, and at a large scale, the aim is to have at least, 2% of the energy go to the pumps, at most, sorry. And then I would like to acknowledge, Josh and the Fair Battery team, Kirk, our chief engineer, the organizers of the conference, and then this entire initiative is financed by NLNet's NGIO and Trust Fund. So thanks to NLNet for their support.